When we interpret gravity data, we attempt to correct for the known or expected geographical effects so that our maps and profiles show only the anomalies. A gravity anomaly, such as a free air or Bouguer anomaly, is the difference between the gravity field data and the background subsurface model. With Bouguer anomalies, we attempt to remove the gravity effects of topography. Our goal in interpreting gravity data is to separate topographically related elements in field data from the gravitational geologic anomalies. To do this, we must consider how our gravity measurements are affected by latitude, elevation, and rock density. We'll begin with latitude. Because Earth is not a sphere but an oblate, the distance from Earth's center of mass, ME, to the surface of the equator, RE, is greater than from the center to the surface at the poles, RP. In other words, the equatorial radius is greater than the polar radius. This distance disparity results in the equatorial gravity being weaker than polar gravity. Thus, the gravity at the poles is about 983,000 milligals, but due to Earth's equatorial bulge, gravity at the equator is only about 978,000 milligals. We can use this equation to calculate the expected gravity value at a given latitude. G equals the gravitational acceleration in milligals, and phi equals the latitude. Next, we'll look at how elevation changes affect gravity. Intuitively, we would expect gravity to decrease as we move farther from Earth's surface, and therefore farther from Earth's center of mass. In fact, gravity decreases by 0.3086 milligals per meter for every meter in elevation. The elevation h is measured in meters. This calculation does not include any mass between the observation point and an observation datum, usually sea level. We call this gradient the free air correction. For example, we can calculate the expected gravity value at the top of the Burj Khalifa building in Dubai, UAE, one of the tallest buildings in the world. The height of this building to the very tip is 830 meters. It is located at a latitude of 25 degrees, and our observation datum is sea level. Using the International Gravity Formula equation, and knowing that phi equals 25 degrees, we can calculate a gravity value at 25 degrees latitude of 978,960 milligals at the base of the building. Using the free air gradient, we determine that gravity is 256.14 milligals less at the top of the building. Therefore, we would expect gravity at the top of the building to equal 978,704 milligals. The most critical source of error in land gravity surveys is the inaccurate measurement of elevation at the survey site. To accurately predict gravity at the survey site, we must know the elevation of the site precisely. Achieving a free air correction accuracy of 0.01 milligals requires that we must know our elevation to within 3.2 centimeters or just over an inch. Now we'll explore how changes in rock density affect gravity measurements. With rock densities, our goal is to produce a map that is free of correlation with topography, unless the topography directly correlates with subsurface geology. To do this, we apply a Bouguer correction to produce an anomaly map. The map indicates subsurface density variations caused by geologic structures. This correction is designed to compensate for the attraction of rock between our observation datum and the observation point. For example, if we're measuring the gravity at the top of a television tower on a big hill with an observation datum at sea level, our measured gravity value at the top of the tower will increase. The basis of the simple Bouguer gravity correction is to approximate the gravitational effect of the rock between the datum, sea level, and an observation point at the top of the hill. We do this using an infinite slab of some density. We call this density the Bouguer density, which is used in the Bouguer slab correction equation. To simplify our calculations, we can combine the free air correction and the Bouguer slab correction into a single elevation factor, F, for the free air correction, minus B rho for the Bouguer slab correction. Here is the elevation factor equation. Note that this equation is used when the elevation, h, is measured in meters. For this example, we have calculated that h equals 803 meters, the distance from sea level to the top of the hill. Using an average bouquet density of 2.67 grams per cubic centimeter, the elevation factor for our example equals 157.95 milligals. This video has shown how to correct for expected variations in the gravitational field using free air and bouquet corrections, and how to separate topographically related elements in the field from geologic anomalies.